Welcome back, everyone. So you ready for some more Parse? Up next is running at scale on Parse.
Hi, F8. Yeah, that font is too big. She told me to just tell her, so shrink, or scale. All right, whatever. We'll figure it out. Welcome to our talk on perfect. Thank you. On building scalable apps on Parse. My name is Charity. This lovely boy here is my co-presenter, Thomas. And let me tell you just a little bit about ourselves. I lead the production engineering team at Facebook that works on Parse. Basically, we're responsible for tackling most of the back-end scalability and reliability issues. When something goes wrong with an app, often in the middle of the night, we are the ones who get paged. We wake up, we figure out what's going wrong. We do a deep dive in trying to figure out what developers are doing and why they're doing it and how we can solve those problems. And then most importantly, we try to take the solutions that we've come up with and try to apply them broadly across the platform so that everyone can benefit from them. Tom is a software engineer on the back-end team. He's been on Parse for over 3 years at this point, basically since before beta, around beta.
Before we exited,
yeah. He's a full-stack developer. He's done pretty much everything. He's built mobile apps. He designed and built the entire push platform. Lately, he's been doing a deep dive into the next generation of Parse databases and storage solutions. So if you've ever used Parse, oh, I need this thing, don't I? You know that this is basically our pitch to mobile developers, right? Parse is magic. You, as a mobile developer, you don't actually have to care about things like data centers, packet loss, network latency, hardware provisioning, stateless services, data models, choosing indexes and shard keys. All of that really messy backend infrastructure stuff, we do it for you, right? And you know what? It actually works amazingly well. Most of the time, we've gotten really good at solving these problems naively for mobile apps at scale. We host over 500,000 apps now, and that includes just a vast diversity of types of applications. We have social apps, we have gaming apps, we have messaging apps, we have real-time, we have things that have write-heavy load and read-heavy load. So we've gotten really good at scaling mobile apps. In fact, our aggregate API request weight has been doubling every couple of months for as long as Parse has been around, which, if you do anything related to backend engineering, you know is a relentless rate of growth to maintain. And at the same time, as we've been supporting hockey stick growth, over the past 6 to 9 months, our reliability has improved by over an order of magnitude, and we are really fucking proud of that. So basically, we have a team of world-class infrastructure engineers who are dedicated to solving your problems at scale. And so when you use Parse, you have some of the best engineering resources in the world who are working on solving your problems. And that can feel like magic. But here's the thing that every developer knows. There's actually no such thing as magic. Once you reach a certain scaling inflection point, you have to understand some things about your network topology, your architecture, your storage layer, and your data model in order to sustain your rate of growth. So there's no such thing as magical scalability. I wish there were, except for the small fact that then I would be out of a job. Scalability is hard, and there are hard engineering trade-offs to make. Over the last 3 years, Oh my God, we have seen it all. Like, we have seen apps where we had never heard of these guys before. We wake up one morning, and they're suddenly the #1 app of Parse. Like, they 10x'd, or they 20x'd, or they 30x'd overnight. They got featured in the iTunes store. They got, like, a bunch of press that they weren't expecting. And they literally, like, multiplied by 10x, 10x times multiple times overnight, whatever, math hard. Anyway, but we woke up, like we didn't get paged. Nothing broke. Latency didn't go down for these apps. Everything just happened magically on the back end. And this is a sign. This is a sign of a really solid, well-designed app that was built to scale. On the other hand, we've seen some apps do some less good things. We've seen some apps do some things that are just flatly impossible to scale. We've seen apps that have performance problems when they hit tens of users, hundreds of users. Generally speaking, these are apps where like the request times scale linearly with the amount of data that they have, which implies that they're doing a lot of full table scans. So one day, like, you've got 99 users, and the app is working perfectly fine. The next day, all of your triggers are timing out because you have 105 users. People start filing tasks like, oh my God, Parse is down. We're like, we dig into it. We're like, oh, dude, you're doing like 10 round trips of full table scans, and you just like tipped over a cliff. So there are some things that we can do on the back end to help, and we'll talk about those, and we do try really hard to make this magic. But there are even more decisions that, like, only you, only you, the mobile developer, have the power to make. And it can make all the difference to whether your app will seamlessly scale up to hundreds of users or tens of millions of users and beyond. So, like I said, as you scale up, you have to have more knowledge and awareness of what's under the hood to make good decisions. So Thomas and I want to talk about what's under the hood and help you make good decisions. We're going to focus on two main scaling points here. We're going to talk about how to improve your cloud code experience. And then we're going to talk about databases. We're going to talk about how to write efficient queries and how to model your data in ways that won't bite you in the ass as your data set grows. So let's start by looking at the path of an API request. I had actually had a diagram of Parse's infrastructure, but you know what? It looks like spaghetti. It's very hard to reason about. We're just going to call that magic. What I can show you is the critical path of a single API request. Here's what happens to an API request when it comes in from the internet, goes to the load balancer, hits the API request. API server says, is this a cloud code function or is there a trigger? Goes to cloud code, and then it decides, do I need to talk to the database? If it needs to mutate objects, it goes back around. So Thomas is actually going to start out by giving an overview of cloud code performance.
So, for those of you who don't know, cloud code is your code running the Parse SDK in our infrastructure. And it comes in 3 major variants. First, you have triggers, which allow you to weave your code into the natural data flow of your application. You can use this to validate a save before it happens, so you can catch someone trying to cheat in your game. Or you can respond to a delete and clean up dependent objects. Or respond to a message being saved and send a push notification. Next, we have cloud functions. And these create complex endpoints in the Parse cloud. They're a great way to make your service available to other third-party services. For example, a cloud function can be used to receive an SMS sent by Twilio. It's also a great place to encapsulate any proprietary business logic that your app relies on. If your app fundamentally depends on some secret sauce, you should move it into a cloud function and not ship it with your client code. Because over time, you should expect that you'll become more sophisticated. You may make your app either faster or better target your users, and you want that change to be reflected immediately. If it's shipped as part of your application, your users won't benefit from your innovation until they download a new copy of the app. But if you ship it with cloud code, then once you make a change, that value is given to all of your users instantly. And finally, we have background jobs, which allow you to perform sophisticated data analysis or migrations periodically. But for today, we're going to focus on the first two of these, because these are the things that will most directly impact your end user experience. Now, you'll notice that they have a 3 and 15-second timeout, respectively. Occasionally, developers ask me if we can increase the timeout for these parts of Cloud Code. But that's not actually the right approach. Because frankly speaking, if you're staring at your phone and it has a little spinny wheel for 15 seconds every time you want to do something important, that's a pretty crappy experience. So rather than asking to increase the time limit, which we are willing to have our customers be bored, we should try to figure out why Cloud Code is slow and instead address that issue. So in order to understand Cloud Code performance, it's helpful to understand its architecture and the tools that we have in order to make our apps faster. Cloud Code is built as an isolated sandbox. It's based on Google's V8 JavaScript engine with additional layers of isolation added on top. Now, it would be a pretty poor sandbox if this had direct access to the database. So that means that we have to make sure an API request goes through that entire architecture diagram all over again. This is absolutely critical for reliable and consistent security, but it means that we have to be aware of how many API calls we're making from within Cloud Code. Now, we're going to look at some code examples today and how we can optimize them. All of these source code examples will use JavaScript promises. If you're still using callbacks, I highly recommend that you learn how to use promises and even migrate your entire code base. Promises are much more composable than callbacks, so you can have much more sophisticated code and still have something that's easy to reason about. You can remove redundant error handling because promises allow you to have something that's almost like a try-catch block. And today we're going to learn how to use promises to remove redundant API calls entirely or to parallelize your request to make your app faster. So let's look at an app that makes too many API requests. This is a before save trigger. So anytime the kitchen object is saved, we want to check if there's too many cooks. So this one line of code is actually spoiling the performance of our application. And why is that? Well, let's go back to our server diagram. We had a request that came from the general internet, and the load balancer found us an available API server. Because we noticed a before save trigger, we have to go to Mongo and figure out what the previous state of that object was. Then we find an available Cloud Code server and open an isolated environment for your app to run in. But we ran into that line of code, which needs a new API request. So we don't go through the general internet. We have some small optimizations for you, but you still have to get another API server. And that API server is going to have to create another Cloud Code server for you to use. And that's not even counting the cost of what this parse cloud function is going to even do. It has to do all of that before you can start unwinding, freeing up control back to the API server, and then eventually following the path back to that original Cloud Code function. Once that completes, we can finally return control back to the API request, save the change back to Parse, or to the database, and then hopefully you're not doing this all over again in an after save trigger. Because we finally have to complete that process before giving control back to your app. So this is obviously a bad idea. So what can we do to fix it? Well, it's easy. We'd simply replace our parse cloud function with a JavaScript function. This will avoid us needing to go into a new Cloud Code isolate needlessly. In fact, whenever you have a cloud function that's a good utility function, you should define it in terms of a JavaScript function and make sure you use that JavaScript function everywhere within your source code, inside of Cloud Code. Let's look at another example of some code that makes too many API requests. Here we look at too many cooks itself. This may look well written, but let's dive a little deeper into get cook count and get kitchen limit. These functions also may look like they're well written. They're terse, easily read, but there's some redundancy here. They're both making the same API call, so we're wasting resources. Ideally, we would want to factor that out and only use that line of code once. And obviously, we know how to stop repeating ourselves from a code perspective. We can factor this out into a utility function. But when we call getKitchen twice, we're still making 2 API requests. But some JavaScript hackery can actually fix that for us. First, we're going to save the promise that query.first returns. Next, we are going to actually rewrite Git Kitchen so that it returns that promise outright. In this line of code, that Git Kitchen is the same as that one. We've actually changed the way our program works to cache the result of this API request. When we call Git Kitchen twice in a row, both parts of this code flow are going to block on the same network request and then run in parallel afterwards. So we've actually made our application cheaper and faster to run. Now, a major problem I see all over cloud code are serial requests. Serial requests are latency killers, and they're hiding everywhere. When you see the word then inside your code, that actually means sequence. We are first querying appetizers and then querying desserts, when appetizers have nothing to do with desserts. So why can't we run them in parallel? Ideally, we would like to strip out this structure, because all we care about is getting appetizers, getting desserts, and then returning that result. And we can do that with parse.promise.when. When will take any number of JavaScript promises, and its success callback will return the value of all of those promises. So you notice that we're now only making one round trip to the server, which will make our program almost twice as fast. So these are great ways to make sure that you can do more within your time limits, but it's very important to remember that time limits are not actually the enemy. Time limits are there to protect you, because by the time you're hitting a 3-second query limit, you're already having a bad user experience. So you really should optimize your query patterns. And Cherry is going to take over and lead how we can optimize our database.
My favorite topic. This is a thing that I get woken up in the middle of the night for the absolute most. So opinions, we have them. So there are a lot of things that you can do with Cloud Code to improve your app's performance. Thank you, Thomas. But to be truly scalable, every single request needs to be efficient as well. And in our experience, the vast majority of performance problems can be traced back to the database. So we'd like to talk a little bit about how a database works, also how our database works in particular, and how you can leverage that knowledge to write more efficient and scalable queries on our platform. What is a database? Hopefully this is not news to any of you. Basically, a database is made of 3 building blocks, right? You've got your data store, you've got your indexes, and you've got your query planner. On Parse, our primary data store for application user data is MongoDB, which is a document database. So we're going to use some Mongo terms, like collection and document. For those of you who are more familiar with the relational database world, a collection is basically a table, a document is basically a row, and columns are basically like keys in the documents. We actually have one of the largest and most complicated MongoDB deployments into the world, thanks to all of you folks. MongoDB runs in replica sets with an elected primary and multiple secondaries. And we have dozens of replica sets. And we allocate anywhere from a few apps to literally tens of thousands of apps per replica set based on the workload composite and various top-level metrics like lock percentages. So you can kind of think of a document database like a cookbook. Like, the documents are like recipes, and the indexes are kind of like appendixes. So these are kind of the database principles that we want to talk about. We want to talk about how to write good queries, how to minimize the amount of work that the database has to perform on your behalf. We want to talk about how to construct a scalable data model, and why object sizes really matter a lot. And at the end, we're going to delve just a little bit into some of the magic that Parse performs behind the scenes to help your workload perform better and scale more gracefully. So let's start with how to write good queries that can actually scale. Writing optimized queries, probably the #1 most important thing that you can do to build an app that scales. So how do you do that? The golden rule of writing good queries: scan as few records as possible. It's all about reducing the search space and making good use of indexes. When you have a small amount of data, like, you can write almost any query at all, and it will be OK. You know, you have 100 documents. You just ask for them all. It's fine. If you have 10,000 documents or 10 million documents, your queries are just going to start timing out, and you're going to be like, well, Parse is down, or you're just going to be like, well, my app was built badly. I'm not sure which, but probably one or the other. Anyway, you can forget about scaling up to tens of billions of records. The best query in the world will always be a point lookup for a single object ID or an index that only returns one result. That shit will scale. The worst query, technically not the worst query in the world, but we won't get into that because it's outside of the scope of this talk. But a very, very bad query is a full table scan, and this will never scale, right? This is a real query that I swear to God we have seen in the wild. We have seen people do this. And what you are basically saying is, hi, Mr. Recipe Book, give me all of the recipes that take less than an hour to prepare, or exactly an hour to prepare, or greater than an hour to prepare. You have to read the whole fucking cookbook. Is that how you want to make your dinner? Don't do that. If you're not dealing with point queries, you're dealing with range queries. And the key to range queries is reduce the search space. This means you need to think about indexes and how your data is laid out. I'm going to get to indexes. I'll talk about indexes and how we intelligently do smart indexing later. But the key to efficient range queries is to be selective. So think about, ask for what you want. Do not ask for what you don't want. And always make what you want as small as possible. Here are some questions you could ask your cookbook. Give me all the recipes that are appetizers. Okay, 30%. Give me all the recipes with cinnamon. Maybe 12%, so that's better. But we can do better, right? We can combine restrictions, which allows us to create a compound index, which reduces the search space to the intersection of the two constraints. Let's talk some more about some specific anti-patterns. Here are some terrible things that you can do to a database that will never, ever scale because they are either hard data problems or hard operator problems. Hard data problems. No database is ever going to be able to efficiently answer these questions, right? There's a great little visualization of all of the recipes that you're asking for. It's not going to work. Greater than and less than, this is trickier, right? It depends on the data that you actually have. If you're asking for recipes that take, more than an hour to prepare, maybe you've reduced your search space by 75%. If you ask for recipes that take, less than 5 minutes to prepare, you've probably reduced your search space by a lot. So this is kind of a great example of where, we can give good principles, but we can't exactly tell you what to do with your data because you are the experts on your data, and only you can know if things like greater than and less than operators are good or evil. Then there are the operator problems. Sort of related, sort of different. If you're saying, give me all the documents that don't match this one thing, or give me all the documents that don't match this list of things, you're basically just telling the database, do a full table scan except for a couple of documents. Basically, whenever you're using the not and operator or the not equals to operator, you've lost the war. Just don't do it. And if you're saying, give me a list, give me all the recipes which may contain a word, you're doing a full table scan because you have to read all the recipes to see if it contains it or not. We just can't make full table scans performant. It's like asking us to break the speed of light. You have to look at your data and do this for yourself. The things that you can efficiently ask a database, our database in particular, are these things. Point queries, use them whenever you can. Equals, love equals. Range scans, find objects in a range that successfully reduces the search space of a scan, great. And you can ask the database to return objects in a particular order. But you really probably need to be ordering them by the same key that you are scanning on. And this is a Venn diagram, by the way. You can efficiently ask for any overlapping set of questions there. Which brings us to the ordering topic. This is perhaps not the best visualization in the world, but here are two different indexes of the same data in the opposite order. So if you take the first one, and I ask you to find how long it takes to cook cereal, you can do that really quickly using the first index. You don't even need to look at the document store. If I asked you to list all of the recipes in the order of name, you could also do so with the first index. If I asked you to list all of the recipes in the order of prep time, you can do that with the second index. You can even ask for all recipes that take, less than 10 minutes, sorted by prep time. You can't use either index, though, to look up recipes that say, start with the letters A through M ordered by prep time. The reason for this is because the index won't be in the same order if I change my request to ask for recipes that start with the letters A through C ordered by prep time. The range of recipe names I'm asking for actually changes which recipes should be considered, so there's no way to store them in the correct order in an index. This is kind of another way of visualizing the same problem, right? Thomas loves to say that ordering is one of the most sadistic things you can ask a database to do. You must either use an index that already returns the results in sorted order, or use an index that successfully limits your result set, and then you sort it in memory, which also Mongo has constraints on doing. You only get 64 megs, and then you're swapping out to disk. It's bad. Anyway, if your selection criteria isn't the same as your sort criteria, your indexes can't help you very well. And this is especially dangerous when you have non-overlapping data sets. Consider this game. Most players are entry level, and most players have logged in recently. We can't use a single index to do both restriction and sorting, so we have to choose either index. If we choose the player level index, we have to sort documents in memory. If there are many players in the range we're looking for, sorting in memory can be extremely expensive and can even fail. You might want to consider doing that client side. If we use the last login index, we'll yield results in the correct order, but we'll have to ignore users who aren't in the right level range. So you have two choices, right? The first option is slow if there are many users in our level range, and the second option is slow if there aren't. There's no way that we at Parse can naively optimize this query without intricate knowledge of your app's data. The last thing I want to say about constructing good queries is about counts. Counts are expensive and bad. Mongo doesn't have counting B-trees, so every count that you do will scan all counted documents. Now, they can be fast if you're using an index and you're reducing your search space, and so you're just effectively scanning that small set of documents that you're counting. But otherwise, you're back to our old friend, the full table scan. This is the reason that we heavily limit count queries in our API. They're really convenient. I totally get why you would want to use them a lot. And we're working on database engine improvements that will make this problem go away, and you're going to love it. It's going to be amazing. but for the time being, they're really expensive. And a better strategy, if you can all handle approximate counts, is just to use Cloud Code or a background job to update a count value in a collection and just query that single count value. So let's talk a little bit about indexes, because indexes are part of the magic that we do for you on the back end of Parse. I actually have a whole blog post out there, how we're doing indexes now, and we are in the middle of figuring out how to do them differently and better, but I'll explain how it works today. First philosophy, unindexed queries are death. So we do our very best to ensure that that never happens. For every API that comes into Parse, we ensure that it has an index. For simple indexes, we basically look at that API request. We look at the operator usefulness and the data type. And we try to guess which indexes are going to be most effective at reducing the search space for that query. If the operator is an equals, it's probably great. If it's a less than or greater than, it's probably good. If it's a prefix match, also great. If it's a not equals operator or a not in operator, it's probably a bad index, and so we heavily demote it. And we do a similar thing with the data types, right? Strings are great to index. Arrays are great to index. Numbers and Booleans tend to have less entropy, so we demote them. We also have a nightly job that analyzes your real API request data and generates what we believe will be the best compound indexes based on your traffic to give you better performance. in general, the more tersely that you can articulate your query, the more performant it will be. You should avoid nested ors and massively auto-generated in clauses. I feel like I'm running a little over time, so I'm going to skip through some of this. Why should you care if you're creating a lot of indexes? Basically, if you're querying on a bunch of shit, it's going to build a bunch of indexes, right? Because we're looking at your API queries. Why should you care? Because write performance. Basically, your write performance will decrease linearly with the number of indexes in your collection. So, one practical consequence of this is do not auto-generate columns and query on them. You will screw yourself. A lot of developers have been asking for a more transparent way to view and manage indexes, and we totally hear you. Like, we're working on it. Simplicity is your friend. If you're querying on a lot of things, we're going to index a lot of things, so try not to do that. Yeah.
So,
turn it over to Tom.
So I'm going to talk about a more fun topic, laziness. Laziness is good. Laziness is a virtue. Because you can't actually make software faster, you can only make it do less. So being lazy is actually just as important as being efficient. So you should make sure you do as many reads and writes as you need and no more. As Charity likes to say, take your gut estimate and cut it in half. That's probably accurate. One of the most common problems I see with these are the type of queries that people issue at your program startup. The reason this becomes a problem is we forget sometimes that with a mobile app, the OS is allowed to kill the app as it goes into the background and start it up again as it goes to the foreground, which means that in the hands of a real user, your application startup logic probably happens vastly more often than you expect. This is bad, but it can actually go to catastrophic if your app encourages everyone to log in at the same time, either because of a schedule or because of a push notification. So when you have an app that encourages 1 million people to log in at the same time and issue the same stupid query, you are going to hit a burst limit. So the way to fix this is to add caching. And caching is really easy to do. Here's the way you can do it in iOS using our older method called query caching. This code says that I want to make sure I use a cache whenever it's possible and otherwise go against the network. But I will only consider that cache valid if it is no more than 24 hours old. Now that 24 hours is a trade-off that you're going to have to make for your application. The larger it is, the more you're going to save, the more your database is going to love you. But the longer it may take for you to actually roll out changes to all of your users. In iOS and Android, you also have a newer method available to you known as the local data store. With this, you can have almost a sub-copy of Parse on your phone. You have objects that can be saved, and you can choose whether to run your query against the cloud and get the most fresh results, or to run it against the local data store. So in that model, if you had run your query within the last 24 hours against the cloud, you would instead say, query from local data store. Now, oddly enough, one of the best ways to improve your reads is to also improve your writes. Because when a database accepts a write, it has to lock the database. It cannot accept any more reads or any other writes until that write is complete. So mitigating the cost of a write is absolutely critical for database performance. There are two things to consider: how frequently you're writing and how expensive those writes are. As we've already covered, an index must be maintained during a write, and that's why we had that graph we showed you earlier. The more indexes you have, the subtly slower your writes will get. The subtly slower your writes are, the subtly longer you will hold the read lock. And the subtly slower both your reads and writes will become. Yet at the same time, you need indexes to prevent your queries from being catastrophically longer. So you have to strike a balance here. Make sure that you have a query pattern that's useful to you and enough indexes that you need, but not something so diverse. Don't auto-generate your column names. Now, next, you can reduce the consequence of a write lock by simply writing less often. I have seen Parse customers that honestly save the same object every 15 seconds, no matter what. That's obviously wasteful. A more subtle variation of this problem, though, is when they set an object to its current value. Parse is smart enough that when you say save, if nothing has changed, we don't actually do anything. But if you set any value, even to its current value, that takes away the optimization. Because we interpret that to mean, I want this value to be 5 no matter what has happened in the background since then. So if you don't have these sorts of concerns about what may have changed in the background, try only changing an object when the value has legitimately changed. And that will cut out writes. Finally, another great way to optimize your write patterns is to buffer it with a local data store. So imagine a recipe app. When a chef is creating her recipe, you might save data every step of the way. You can, after every step that is created, pin your object to the local data store. That way, if your chef leaves the app to look up some research, she won't lose her progress. But then when she wants to publish the application, or the recipe, and make it available to everyone else, that's when you would actually save it to Parse. And the code for this is very straightforward. More frequently, you will say recipe, pin in background. And that will make sure that the recipe is saved to disk and will not be lost. It can also be queried by these queries against the local data store. Only when you want the recipe to be available to others do you actually need to say recipe save in background or save eventually. And that will make sure it hits the Parse cloud. One of the more subtle aspects of write concerns is that the cost of a write is not actually proportional to the amount of data you've changed. It's actually proportional to the size of the entire document. This is a very critical thing to understand. And the reason for this is pretty intuitive, actually. Because when you read an object, you don't want to have to look up the entire history of that object to recompose its latest state. You want to get that latest state and just go on with life. So that means that when you make one small change, you increment one number, you actually have to save the full set of that document back to the document store. But it's worse, because the document store will keep this database consistent. It'll help that database recover from restarts. You also need to save to the op log. The op log is a transcript of every change that's happened to a database, and it's used to keep the secondaries up to date. So when you change that one number, you actually had to save the entire recipe to disk twice. So let's use our newfound knowledge to optimize a data model in Objective-C. If this were a recipe class, well, how could we optimize it? One of the first and most important things is to replace that NS data. Get it out of your object model. It should instead be a PF file. Because PF files are stored by reference, which means your documents will still stay small. PF files also have other benefits. Their URL has version information in it, which means we can really aggressively cache that. So you save on bandwidth and API requests. If these PF files have images in them, we also have UI tools that will help you display an image with a watermark that's there until the file is available. So what's next? Let's assume that this recipe were a recipe for spaghetti. It's very simple, it's very static, it's not going to change. But everyone has an opinion about it. So everyone's going to be appending to that reviews list, which means that the size of this recipe will grow without bounds. Eventually, it will take a long time to save your comment about a recipe because you have to save every other comment anyone has ever made before you. This also means that downloading a recipe can be very expensive. So the solution is to simply split recipe out into review out into its own class. This way, each review points back to the recipe it is talking about, and each save doesn't have anything to do with any prior review you've seen. This keeps all of your writes small, and your reads can also be more powerful. You can say, I only want the most 100 recent reviews, or the 20 most relevant, which makes your app not only faster, but better. Finally, it may be too late to save your object model. You may already have large data. You may not be able to fix write performance, but you can help reads. Using the select operator or select keys operator in iOS and Android will allow you to reduce what part of your object you're asking for. In this case, we're no longer downloading the reviews or the files because we only need name and ingredients. So to recap the rules for having a scalable data model, you should be very, very critical of writes because writes will impact both read and write performance. You should be very critical of your document size, especially any documents that have large binary blobs, because those should always be inside of a PF file. And if you have a large collection, consider splitting it up into two cohesive concepts, especially when you have one section that is large and fairly stable, and another section that is very small and volatile. That way, that volatile section will take a write lock for a shorter period of time. And if it's too late to shrink your object model, you can read less by using the select operator. Because you see, we live in the real world, which means that we have to face real trade-offs. And if you plan your object model to reflect the trade-offs that are inherent in your needs, you can plan for how you're going to scale. If you fail to make a plan, these trade-offs will surprise you. Because once you reach the scaling limit of a database, you cannot get any of these opposing factors without giving something else up. Because read throughput, read diversity, write throughput, and document size all oppose each other. So imagine you're writing a logs collection. You would want to optimize for write throughput because that's what's going to happen most. Shrink your document size. Don't worry about read throughput because you have fewer analysts than you have devices. On the other hand, if you have a news feed, you're going to read more often than you write, but neither will happen at the same scale that you're going to write your documents. This gives you some headroom to either make more complex documents or find news feeds in more complex ways. So we're almost at the end here, but lastly, I wanted to hand it off to Charity, who's going to talk about some of the magic we do behind the scenes to make sure that you improve or have an improved experience whenever possible.
Yes. We do a lot of work on the back end to try and make 500,000 apps play nicely together every day. Some of it is kind of secret sauce, and some of it I can talk about. So in the less than 4 minutes I have remaining, let's see what we can get through. Where the magic comes in. First of all, burst limits. All right, cotenancy. Let's just talk about cotenancy problems for a moment. Parse is basically the one giant cotenancy problem from hell. 500,000 apps distributed over dozens of replica sets. So the first thing we do is we implement burst limits to prevent individual apps from starving other apps of resources. We can provision enough capacity to handle the burst limits that you've defined for yourselves. But it takes time to move data around. So burst limits are important because A, they protect you from unexpected spikes that you have to pay for, and B, it helps us provision enough isolation and capacity. We've also implemented a lot of really sophisticated introspection into our database statistics, like our read locks, our write locks. We log every single query, and we have the ability to see which indexes are getting hit and do a deep dive into all of the queries that every app is performing. We also we limit expensive operations like counts and regular expressions, things that we know are bad and can cause rapid cascading failures. Often these are things that people really want to do, but trust me, it's for your own good. Until we get a better database engine, it's just the way it is. There's also a category of database optimizations that we do for you on the back end. For example, we've found that Mongo Query Planner does not do nested ORs very well. So we often just I see somebody shaking his head. So we actually unpack those nested ORs in the API server, run them, merge them, and return them to you. We limit the length of time that a query is allowed to run, which prevents runaway queue growth, and also just kind of makes sense because you've got an HTTP request that times out after 60 seconds. Well, that query keeps on running. Kill it, right? This helps queues from filling up, which is one of the main things that you can do to prevent congestion on your database. We enforce scan limits. We have a whole bunch of knobs that let us do things like offload some queries, expensive reads, to secondaries if the primary gets overloaded, which helps. It sacrifices some consistency for performance in the short term, but it's a really nice way of degrading gracefully instead of the app hitting a cliff and going down. And since the version of Mongo that we're currently using has a database level lock, we distribute apps evenly across lots of databases to take advantage of better locking. These types of knobs are important because they catch cascading failures and nip them in the bud before they take lots of apps down. So to recap, you should parallelize your API request from Cloud Code. Simplify your queries. Use small documents, please. Optimize for the smallest search space. Use local caching. Batch your writes. Do whatever you can to make the database do less. These are basically the sacrifices that you can make to the scaling gods. And again, they're suggestions and they're not rules. Like, you know your data better than anyone. You know what you're trying to do. Sometimes rules are meant to be broken, but you should know what you're doing before you break them. So is Parse magic? Well, we do try really hard to make it seem that way for our developers. And if you're small, you can get away with a lot. But you should never build your app with the expectation that you won't need to scale. So this is really what we try to do for our developers. We try to make it magic. We really want Parse to be the magical experience for everyone. And they cut off my fucking speaker's notes, so I guess this is the end. There we go. We were going to do Q&A, but we ran slightly over time. Thomas and I will both be at the Parse booth in the garage.
The garage, yeah.
Yeah. So if you have any questions about optimizing your apps, feel free to come and grab us.
Thank you.
Thanks.